So we start our last seminar in this semester, and we're happy to have John Pardon from the Simons Center for Geometry and Physics, Universally Counting Curves in Calabi-Yau threefolds. John, please.
Thank you very much. I'm very pleased to be able to give this talk. So let me share my screen with the slides. Go ahead a little bit. Okay. Yeah, so my title is Universally Counting Curves in Calabi-Yau threefolds. So first of all, what do I mean by counting curves? Well, we suppose we have a smooth projective threefold, then has some curves in it, some one-dimensional subvarieties, and we'd like to count them. So to do that, though there are lots of ways of doing this. One way, which gives rise to so-called Gromov-Witten invariants, would be to consider this space M prime of X. That's the space of stable maps. So that's something like the set of maps U from some nodal Riemann surface to X in a given homology class as maybe some incidence conditions. Okay, so that's one way of thinking about a curve. It's the image of a map from some domain curve into X. And the reason we consider the space is that it has a natural virtual fundamental cycle. That allows us to make sense of this number of curves. So here on the left we have Gromov-Witten invariants. But there are many other ways of counting curves, and the one particular other way of counting curves that I want to consider in this talk is due to Pandharipande and Thomas. And they count stable pairs. So I'm not going to say exactly what a stable pair is, but more or less it's some sort of coherent sheaf on X whose support is one-dimensional. Along with some other data as a section. Okay. So these would give Pandharipande Thomas invariants. Now, a remark is that Gromov-Witten invariants make sense in the almost complex setting. So you don't actually need an integrable almost complex structure. You don't need a variety. You just need a symplectic manifold. On the other hand, since the definition of Pandharipande Thomas invariants involves the notion of a coherent sheaf, that's something which, as far as we know, only makes sense in an algebrogeometric or analytic context. Great. So underlying a stable map or a stable pair is a one cycle. So one cycle is simply form a linear combination of irreducible reduced curves.
So you ignore this zero-dimensional part of the PT story.
Right. Yeah. So in PT there's no zero-dimensional part. In Donaldson-Thomas, that's right. There's these zero-dimensional components. And yeah, so what I'm going to describe does not work directly for Donaldson-Thomas invariants, precisely because of these zero-dimensional components. As one could certainly make a small variation on it, which would work. But for that reason, I'm good. That's the reason I want to consider Pandharipande Thomas and not Donaldson-Thomas, because these.
Yeah, but do I remember correctly this condition which you mentioned, that there might be some points which belong to this one-dimensional support as well?
Yeah. So right. So it's not just a coherent sheaf with one-dimensional support. There's also this a section in H0.
Yeah, okay, but Z of X is a pure geometric part. It's a support as an element of, I don't know, Chow group or whatever.
Yeah, it's pure one-dimensional. There's no zero-dimensional part.
Okay.
Okay, so both these invariants are invariant under deformation. They're also functorial under open embeddings, by which I just mean that how to say, if you're looking at the moduli space of stable maps or stable pairs in the neighborhood of some fixed one cycle, then I don't care about what's going on in the rest of the manifold. You might as well just replace X with some open neighborhood of that one cycle. In a sense, that's sort of a special case of deformation invariance for non-proper families. Okay, so the main theme of the talk is that there's really like a universal invariant satisfying deformation invariance and satisfying, it being some way of enumerating one cycles.
What do you call three properties? It's the only thing which I can read clearly.
Yeah, let's see. I guess it's so coming from some cycle on the space of one cycles, deformation invariance, and functoriality under open embeddings. Although that's really a special case of deformation invariance, so maybe I should have said two properties. Right. So, okay. So what's this universal invariant? Well, we're just going to define some sort of tautological group where it's valued. So you should think of this as being very analogous to the Grothendieck, the universal Euler characteristic of vector bundles is valued in the Grothendieck group of vector bundles. You just take all vector bundles and divide by additivity under short exact sequences. So we're going to do something similarly tautological here, but for one cycles in Calabi-Yau threefolds.
And John, I was kind of confused with the logic. So whatever these invariants will be, this Gromov-Witten and PT invariants will be special case, or what?
Let's see. So maybe I'll skip ahead here and show this equation. So there's some universal invariant which is valued in the Grothendieck group of one cycles, and Gromov-Witten and Pandharipande invariants are homomorphisms out of that group.
Okay, all right. Yeah,
so
it's kind of it's some morally a bit similar to this motivic story when you have some universal abelian group or a ring and invariants give you some realization. Okay.
Yes, exactly. Okay, so let's define this group here. It's the co-kernel of this map. So okay, so first I just want to focus on this middle group. So we just take the direct sum over all Calabi-Yau threefolds of locally constant functions on the space of one cycle. So let's remember H0 with compact support of some space H. Yeah, this is getting hard to write. H0 with compact support of some space A. This is just a free abelian group on I guess the compact connected components of A. So not all of pi 0, just the compact components of pi 0. So what is an element of this middle group? It's simply a formal linear combination of compact connected components of Z of X for various Calabi-Yau threefolds X. Now, I'm not going to require that X itself be compact. If X is compact, I mean, if X is projective, then well, I guess then Z of X still wouldn't be compact but if you fix the homology class, then it would be compact. And anyway, all the compactness that you need to define sort of enumerative invariants in practice is going to be encoded in the fact that I'm taking compactly supported.
This part is understandable, but the sum over all Calabi-Yau threefolds, it's kind of a category of all. I mean, it's
Well, I mean, pick your So, right. So I guess indeed, if I pick some set representing all isomorphism classes, and take that direct sum. So this middle thing isn't really all that well defined, but the co-kernel will be well defined. Okay, so maybe I should say now then what this group is. So this is the direct sum now over all families of Calabi-Yau threefolds over an interval. All one parameter families of Calabi-Yau threefolds. So given such a family, so this is to impose deformation invariance. I want to say that the invariant associated to the fiber over 0 is the same as the invariant associated to the fiber at 1. So if I have, again, a compact component of this relative space of cycles, then I can restrict it to 0 or restrict it to 1 and get something in this middle group. So I remind you of the definition of the relative cycle space. So that's what goes on here in this. That's what appears here in this group on the left. So this is a point in this relative cycle space is a point in my interval t in delta 1, and then a cycle on x sub t, a cycle in the fiber over t. So that's some space, and inside it you have z of x naught and z of x1. So you can restrict compactly supported functions. Right. Okay. So to answer Jan's question about set theoretic issues, what can I say? So take some set parameterizing all isomorphism classes of Calabi-Yau threefolds. Take another set. So first you fix the first set, and then you take another set which parameterizes all one parameter families of Calabi-Yau threefolds together with isomorphisms between the fiber over 0 and the fiber over 1 with the some Calabi-Yaus in the set you chose first. So it's sort of an inductive thing. First, you have to choose this set, and then based on that set, you choose what this has to be. And then I claim that the co-kernel is independent of the choice. Okay, so it's sort of tautological to see any invariant satisfying deformation invariance is going to give you a homomorphism out of this group. So. And in fact, it's a ring. The Grothendieck and Pandharipande Thomas invariants are ring homomorphisms. Okay, so I should definitely say this definition is inspired directly by Ionel and Parker's work on the Gopa-Kurmavafa integrality conjecture. So they, Gopa-Kurmavafa conjectured some rational linear combinations of Gromov-Witten invariants are always integers. And Ionel and Parker proved this for Calabi-Yau threefolds, some symplectic Calabi-Yau threefolds. But really what they've showed is something much stronger, which is that any symplectic Calabi-Yau threefold is in some sense enumeratively equivalent to a bunch of local curves. So just isolated, smooth curves of some genus. And in that case, the Gopa-Kurmavafa integrality conjecture had been shown previously, essentially. This is essentially already known. So they didn't phrase it in terms of this sort of Grothendieck group, but if you read their paper, that's basically what they're doing. Right. So this group gives some precise notion of being enumeratively equivalent to Calabi-Yau threefolds with a compactly supported function on their cycle space. You get two classes here, and if they're the same class in this Grothendieck group, then for any reasonable sense, they're enumeratively equivalent. And any enumerative invariant will have the same value. Okay. So there's another level of complication which we need. So I explained this simple version of the Grothendieck group first because it's easier to understand, but it's not the group we can actually prove things about. So basically what I need to do is I want to include higher deformation invariants. So that is, I want to study enumerative invariants, which are not only invariant under deformation, but maybe if I have a one parameter, for one parameter family, I get, say, a cobordism between the two moduli spaces. But if I have a two-parameter family, I get a cobordism of cobordisms. So anything reasonable will satisfy this. And this is the group you write down to encode that. So I just take all Calabi-Yau, all families of Calabi-Yau threefolds over all parameter spaces of any dimension, assemble this into a complex. And I also include not just H0, but all compactly supported cochains on the space of cycles, because a cochain of any degree you can also pair with a virtual fundamental cycle of your whatever enumerative theory you have. So this double complex here, it's a second quadrant double complex. So it looks something like this. It's unbounded in both directions. And this complex I wrote down on this group I've defined first. Well, it's the co-kernel of this map down there. So, or well, okay, no, not exactly. Anyway, it's the group appearing here in the in the spectral sequence you get from this double complex on one of the pages. So another way of thinking about this group is to say, well, okay, I want to talk about this here on the right. Suppose I have a map of spaces, W to B. Now there's a group I can consider, which is the homology of the base with coefficients in the fiberwise compactly supported cohomology. So sort of hard to wrap your head around this group, but if you've ever tried to think about what what F upper shriek actually is, then this is in some sense the answer. If assigns to some open set in upstairs, this cohomology group, cohomology of the base, homology of the base with coefficients in fiberwise compactly supported cohomology. And you could describe it with these various sheaf functors. Right. So if you take say the moduli space of all Calabi-Yau threefolds, imagine that was a well-defined geometric thing, and then over that moduli space of all Calabi-Yau threefolds, you could consider the relative cycle space of the universal family. And this Grothendieck group here is simply this construction applied to that family. It's the homology of the moduli space of Calabi-Yau threefolds with coefficients in compactly supported cohomology of the cycle space of cycles. Okay, so this group, it's not just a group, it has a lot of structure. In fact, it has a multiplication and a co-multiplication. Multiplication is disjoint union of cycles, and co-multiplication is sum of cycles. So that's quite, and it's a bi-algebra. These are compatible. So it's a lot of, at least somewhat surprising to me, it has so much structure. Okay, so the main theorem about this group is, in the setting of Calabi-Yau threefolds, it's supporting degree less than or equal to 0, and at degree 0, it's freely generated as a polynomial algebra by these so-called equivariant local curve elements. So these equivariant local curve elements, they encode the local enumerative theory near a smooth curve in a Calabi-Yau threefold. So what is the local neighborhood of a smooth curve in a Calabi-Yau threefold? Well, by deforming to a normal cone, that's just a rank 2 vector bundle over a curve. So if you have rank 2 vector bundle over a curve, you can ask to enumerate cycles supported on the 0 section. Now that's not really well defined, because in most cases, the 0 section is going to move off of itself. So that's not really a compact space. But there's a C star action just by multiplication on the fibers, which allows you to make sense of these counts. Allows you to make sense of the notion of counting cycles supported on the 0 section. It takes whatever virtual fundamental cycle you have on the space of all cycles, and it lifts it to a cycle supported on the fixed set of the action. The only cycle which is fixed by C star is the 0 section and its multiples. So that's what these equivariant local curve elements are. And so this theorem, of course, it's inspired by Ionel and Parker's result for symplectic Calabi-Yau threefolds. It's a slightly different context, though. They didn't consider this Grothendieck group with higher deformation invariants. They just considered one parameter families. Okay, so there's this well-known conjecture of Wallach, Nekrasov, Okounkov, and Pandharipande relating Gromov-Witten and Pandharipande-Thomas invariants. It's known in many cases, including the case of local curves, and so this implies it's true for all Calabi-Yau projective Calabi-Yau threefolds. Now, I should emphasize that this is not this is far from the general case of MNOP. There's their conjecture is also valid. They also have a conjecture for relating descendant invariants, Gromov-Witten descendant invariants, and Thomas, Pandharipande-Thomas descendant invariants. This theorem doesn't say anything about those, and I'm not really sure how to treat them. Moreover, this theorem is essentially a transversality statement. It's basically saying that if you're allowed to perturb your almost complex structure, perturb your complex structure as generally as you can, then you can reduce an arbitrary enumerative problem to an enumerative problem where the cycles are essentially cut out transversely, right? And then you just get local curves, a bunch of isolated curves. So because of that, it's really limited to this Calabi-Yau setting. or more generally, the semi-Fano setting. So really, this is, I stated the simple version for the talk. There's an analogous statement, just a little bit more complicated, for threefolds whose anticanonical bundle is NAF. So as long as C1 of X evaluates non-negatively on all curves, then there's an analogous generation result.
John, somehow to get an intuition, so you mean that kind of in these both theories, the invariants actually depend on what? On some local neighborhood of curves, of this, I don't know, cycles. How should I think about this XGM?
Yeah, so XGM is simply it's the so if I want an element of this group, right, I could give you a smooth Calabi-Yau threefold and an isolated cycle. So maybe I give you a smooth Calabi-Yau threefold and a smooth genus G curve of multiplicity M, which is isolated in a space of cycles. It doesn't deform at all. So that would be so just the characteristic function of that isolated point would be this XGM.
I see. Okay. And so if you want, for example, to prove their conjecture, then you do sort of computations which involve only these generators, free generators. Okay.
Yeah. So it would be great to generalize this, say something about the general case without the Calabi-Yau assumption. So for negative first Turing class, but I don't have any idea what to do for that. Okay. So
so you said you can do Fano also, right?
Yeah.
And in that case, usually you want to put insertions, right, to get actual numbers. So you can handle also insertions and
so insertions come from putting in will come from all come from cohomology classes on the space of cycles. You take your cohomology class on X, you pull it back to the universal family over the cycle space, and then you do the wrong way push forward down to cohomology of Z of X. Yeah, so if you just put the X comma certain cohomology classes in here, that's an element of the Grothendieck group, such that when you evaluate these ring homomorphisms on that, you get the invariants with insertions.
Okay, thanks.
Yeah, but you can't get descendants that way. You need some other anyway. So that's the issue. Yeah, and of course you could also do sort of these family invariants where you have a family of Calabi-Yau threefolds and you want to count curves which maybe appear in one fiber or something. That's incorporated here since we consider families.
You mean like for like K3, or no? You're restricted to dimension 3, or
dimension.
Okay.
Yeah, I only proved anything for dimension 3. I mean, yeah, the families of threefolds. I guess usually you would consider families if it were negative C1, because then you cycle. So which is the case I can't handle. But if you had a family of Fanos or Calabi-Yaus, we'll also do that. Okay, so let me contrast the settings here. So right now, this theorem I'm talking about is within the realm of complex geometry. Ionel and Parker's result is about almost complex geometry. There you have more flexibility. You can locally perturb your almost complex structure. Because of that, their result is that they can essentially, their methods compute this Grothendieck group, the Grothendieck group that I defined at the beginning, where you just have Calabi-Yaus and one parameter factors, Calabi-Yaus, and nothing else. When I have integrable almost complex structures, right? So what's the difference between almost complex geometry and complex geometry? The difference is, in almost complex geometry, you can find a single almost complex structure, which gives you transversality everywhere on the whole cycle space, makes all the cycles transverse. A generic almost complex structure makes every non-multiply covered curve transversely cut out. That's what goes into Ionel and Parker's result, and that's what would allow you to compute this group, where you just have Calabi-Yaus and one parameter. So in the setting that's a great result, but it doesn't. It's not applicable to MNOP because the Pandharipande Thomas invariants and Donaldson-Thomas invariants are not defined given for almost complex methods. You need an integrable complex structure, as far as we know, to define this, have coherent sheaves. So to say anything about MNOP, we really have to move to this setting, complex geometry. In complex geometry, what's true for transversality is much, much weaker. What's true is that if you have so what is true? So if I have a compact Calabi-Yau, some projective variety, well, for a projective variety, deformations of the almost complex structure, it's deformation of the complex structure, that's H1 of X with coefficients in the tangent bundle. So that's finite dimensional, and it might even be zero. So if you're trying to globally deform the complex structure, this is just, you're out of luck. This is not going to, it's certainly not big enough to get transversality for arbitrary cycles. So what you can do, though, is if you're only interested in getting transversality for a specific cycle. So suppose I just pick a one cycle in my Calabi-Yau threefold, so a curve, a formal linear combination of curves. Now, if I'm allowed to, and I want to work locally near that cycle, so what that means is I'm allowed, and just get transversality on the space of cycles near that cycle. So in other words, I'm going to say I'm allowed to just delete the rest of X and focus just on an open neighborhood of my one cycle. Now, on that non-compact Calabi-Yau threefold, there are lots of deformations of the complex structure, preserving integrability. I'll say what they are shortly. And there's an abundant number of these, and there are plenty to make your cycle transverse, regular, unobstructed. So that's the underlying engine behind the result. And the fact that it only works locally on the space of cycles is what is responsible for needing to consider families over our high dimensional basis. Okay, so now maybe I'll just sketch a little bit of the ingredients that go into proving this, the main theorem. So suppose we have a curve in X. So X is the threefold. Curve is always compact for me. But it's somehow, it doesn't have multiplicity. So all the components have multiplicity 1. But it may be very, very singular. It may be very, very singular. And it's not a stable map. It's a curve to X. So there are no like ghost components. So I have a one-dimensional subvariety of X. I want to give a notion of when it's regular. So let's consider the normalization C tilde. So that's a smooth curve map to X. And that smooth curve mapping to X, it satisfies some conditions, like maybe that's the image. And so the map, maybe this is C, and then I have a map, maybe get a different color. That's the normalization C tilde. That maps down to C. And that map, right, satisfies the condition that at this point here, the derivative vanishes, or maybe right, or maybe C has some point where it's not unibranch, and then C tilde is two separate curves like this, and then this map satisfies the condition that this point and this point get mapped to the same point in the target. So there are finitely many conditions here that this map from C tilde to X satisfies. Derivative vanishing at some points, and various points in the domain getting mapped to the same point in the target. So, but it's algebraic situation. So there are finitely many of these. Okay, so I decided I want to consider the deformation problem of this map C tilde to X subject to all those constraints. So I consider the problem of deforming that map from C tilde to X, but preserving all those properties, all those constraints. And if that's unobstructed, then I'm going to call the curve C regular. Okay, so if C is smooth, then this is just the usual notion of unobstructed. There's only one thing you could say. But if C is singular, then well, this is stronger than the deformation problem of C tilde to X being unobstructed. When you add constraints, it's more likely to be obstructed. So this is a sort of pretty strong thing to assert about a curve. Okay. So a cycle is regular. Sorry, cycle is called semi-regular when its support is regular. And I say semi-regular because this notion of regularity, well, it only considers sort of certain deformations of the cycle. So if I have a cycle like two, like say maybe a node, you can deform the cycle by smoothing the node, and that's not a deformation considered in this definition. Or if I have a cycle which is a curve with like high multiplicity, then a nearby cycle could be some curve with multiplicity 1, but there are many sheets. Okay, so those sorts of deformations are ignored by this notion of regular. So that's what I call semi-regular. Okay, so there's this constructible subset of semi-regular cycles, and it need not be open. At least there's no reason for it to be open.
But is it locally closed or what?
I'm not. I guess I doubt it. I think the best I can say is it's constructible. I'll have to think about whether it's locally close. I doubt it. I think it's sort of a bad set, potentially. I mean, it's constructible, but that's it. I think. Yeah. So the fact that constructible means that if to form this Grothendieck group, we have to take interior. That's very important. Otherwise, it doesn't make sense. We only take the interior of the semi-regular locus, which is annoying because if you include like into a higher parameter family, for transversality in the usual sense, right? If you have something over some base and then you include into a bigger base, you're allowing more deformations, right? So you can only get less obstructed when you add more deformations. So this inclusion of sort of cycles on a base into cycles on a bigger base, it preserves semi-regularity, but it might not preserve being in the interior of the semi-regular locus, because you might, the bigger base allows you the potential of having a sequence of non-semi-regular things converging to something in the smaller base, which is semi-regular, which is in the interior of the semi-regular locus on the base, on the smaller base. Nevertheless, you can define this group, and it maps to this the Grothendieck group in question that we want to compute. Okay. So the semi-regular locus, it's not so great, I guess, but one thing at least we know is we know the dimension, because the dimension you can figure out just by looking at how these curves deform. And it's not so hard to check that the generation result we want is true for the semi-regular. Basically, it comes down to knowing that something of dimension, a variety of a given dimension, has no cohomology in any higher dimension, and that in the top dimension, it's generated by Poincare duals of smooth points. That's what it comes down to. Okay. So this reduces us to showing that this map is an isomorphism. That's what we want to check. And here's somehow the hardest thing in showing that is the following. So so let's explain this enough divisor statement. So let's have a family of threefolds over some base. Base maybe is a simplex or open set in R. And so then I can form the relative cycle space Z of X, B. And so I want to choose a space of cycles whose projection map to the base is injective. So in other words, I'm just saying for each point in the base, use a cycle in the fiber. Okay, in a reasonable way, a reasonably continuous analytic way, constructible way. Constructively associate to every point in the base some cycle in the fiber. Okay, maybe not at every point, but to every point in the base, you associate at most one cycle in the target, in the fiber. Now, what do I want to think about? So we imagine we're looking at some element of this Grothendieck group I wrote down, which is represented by this family and a cohomology class on its space of cycles, which is supported on K. And then what I want to do is define some deformation of the situation, which makes everything in K transverse. Okay, now to do that, what we need to do is choose a bunch of divisors, which puncture all the curves in K. So a bunch of relative divisors. They should be disjoint, and they relative divisor. So the divisor in every fiber, which varies analytically, and which controls all these cycles, meaning every component of the cycle is intersected by one of these divisors. Okay, and to get this set of divisors, I'm allowed to throw away any part of X which is disjoint from K, from these cycles that I care about. Right, because I'm only the cohomology class I'm enumerating with respect to, it's supported on K. So any cycles away from that, any part of my threefold away from that, I don't care about. I'm allowed to throw that away. So this essentially reduces you to sort of a local problem near a given cycle. And to a local problem near a given cycle, well, if you're on a one cycle, you can just choose a transverse divisor locally. That's sort of trivial. But what's non-trivial is making these divisors all disjoint in a family. So if you imagine you have a family of curves, and you want to choose a bunch of disjoint sections. Well, if you just choose a bunch of disjoint, which somehow have a point on every component of the fibers. So if you just choose a bunch of generic sections, they're going to intersect over a codimension 2 subset of the base. So that's somehow what happens here. If I just choose generic divisors, they will not be disjoint. They will intersect generically over a codimension 2 subset of the base. But then the idea is you use induction. So choosing generic divisors reduces you to some other problem for a codimension 2 subset of B, and then you keep. Okay, so I think on the next slide I explain what these divisors are for. Maybe I should have done in the other direction, the other order. But anyway, what I'm going to explain now is this generic transversality assertion. What is generic transversality in complex geometry? So it's the following statement. So suppose we have a X. So really we were talking about a one cycle. So take a one cycle C inside X. And X is now going to be regarded as a germ around C. So I'm going to take a smooth divisor D, which intersects our curve at some point in every irreducible component of the curve C. Okay, so what I want to do is, for your divisor D, take a meromorphic vector field. So there's a sign error here. This should be plus infinity D. Take a vector field defined in a neighborhood of D, which possibly has a pole along D. So then you can use this vector field so X is built by somehow taking a neighborhood of D and gluing that to X minus D. Take the complement of D and the neighborhood of D, they intersect over the punctured neighborhood of D, and gluing them together, you get X. But I can change the way we do that gluing by the flow of any vector field in this space. Any vector field near D, which is singular along D, you flow by that and use that to modify the gluing mark. So it's perhaps best to begin thinking about the corresponding operation just for curves. If I have a curve and a point, and I have a vector field at that point, a meromorphic vector field is a pole just at that point, defined in a neighborhood, then I can take the disk around that point and flow it by the flow of the vector field and reglue it to the Riemann surface. And by doing that, you get sort of the entire local moduli of deformations of that Riemann surface. And it's similar. I mean, this is just a calculation, straightforward calculation. You can see that these sorts of deformations hit are sufficiently rich to make anything unobstructed. Okay, let's see. So it looks like now I'm going to define these equivariant local curve elements. So let's say I have a rank 2 vector bundle over a curve C of genus G. Now, I'd like to make sense of a count of cycles supported on the zero section. Now, the zero section is not isolated in general, and so that doesn't really make sense. So to make sense of it, we use the C star action. So there's a just multiplication on the fibers of E is a C star action. And the fixed set is the zero section. And in fact, for any cycle, the only one cycles which are fixed are the zero section. The only compact one cycles which are fixed by the actions is the zero section. So what that means is that if you have any sort of C star equivariant cycle on Z of X, Z of E will have a canonical lift to Z of the zero section, so it cycles on the zero section. And anyway, this is one way of writing that down. Essentially, it's just some finite take some finite approximation to the Borel construction. And these equivariant invariants are a special case of family invariants for the approximation to the Borel construction. Okay, and you can check that these local curve elements are equivalent to the other things I defined, the YGMs, modulo things of smaller multiplicity. So remember what was the YGM? YGM was, I guess I didn't define it, but let's move up to its definition up here. Yeah, YGM is this Poincare dual of a smooth point of this. So look at a family of Calabi-Yau over some base. Look at the interior semi-regular locus, and take a smooth point there, which has genus G and multiplicity M, and take its Poincare dual. So that is, an isolated cycle of genus G and multiplicity M. And you can, this YGM, this enumerating cycle supported on that isolated curve. So it's basically doing the same thing as it's a local curve. So I call these the geometric local curve elements, and the XGMs, the equivariant local curve elements. So it's the same idea. You want to enumerate curves supported just on a single. You do your enumeration theory for on just a single smooth curve, some multiplicity, which is isolated in some sense. I don't know whether these are equal. I mean, I tried a little bit to prove it. It seems plausible, at least. What can I say about this? So, in the Ionel and Parker setting, they're dealing with almost complex geometry. So the analogous question for them is false. I mean, the YGM. Well, how to say? I gave a definition of YGM up here, but it's not really a definition because I didn't prove it's independent of the smooth point you chose. Right? Maybe it depends on the family and the point, and maybe it's not depending only on G and M. And in the case of when you have almost complex structures, the Ionel and Parker setting, there's wall crossing. It does not. It's not independent of which cycle you choose. Cycles can sort of cross, and there's a one-dimensional, codimensional one walls, and when you cross them, this enumerative content of YGM changes by something of some multiplicity, some curves or cycles to fly off when you're changing the almost complex structure. Now, one might expect that since we're in a complex analytic setting, that any walls that might exist would be codimension 2, and so you can just go around them. Why GM is in fact well defined, but I'm not sure how to prove that. I mean, we're mostly in an analytic setting, but at the same time, the bases that we're considering are these real simplices. So it's a little bit subtle, certainly. Okay, so this shows that, I guess what I've shown so far, sketched so far, is a proof that the XGMs generate. Now you can in fact use an algebraic trick to show that if they generate, then they freely generate. This algebraic structure of having a multiplication and a co-multiplication is very rigid, and you can show that if there's something in the kernel, then you'd be able to produce something in the kernel which would have to have non-trivial Gromov-Witten invariant, and hence it's not actually in the kernel. I mean, the kernel of, you can take the free algebra on these X, G, and map it to this Grothendieck group, right? And we showed that it's surjective. The question is it injective? Yeah. You can use some algebra on this side to produce some. So if the kernel is non-zero, you can produce some element of the co-kernel, which you then push here and realize has to have non-trivial Gromov-Witten invariant. So put that in the kernel. So this does not finish the story. It doesn't tell you everything you might want to possibly know about enumerative invariants of Calabi-Yau threefolds. It does, in particular, doesn't say anything about sort of multiple. Doesn't. Yeah, about multiple covers in a certain sense. So, Ionel and Parker prove in their paper a formula for Gromov-Witten invariants of a Calabi-Yau, complected Calabi-Yau threefold. And if you take that formula and lift it to this Grothendieck group, it's essentially this formula, which I don't know how to prove. But it basically says there's these integers, E, beta, comma, G. In a sense, the number of embedded curves of genus G and homology class beta. And for each such curve contributes this power series to the Gromov-Witten invariant. Okay, so you just multiply all of those together, and that's the total Gromov-Witten invariant of your Calabi-Yau threefold. So that's what they prove. They prove this for Gromov-Witten invariants. And I would conjecture that the exact same formula holds in this Grothendieck group. But how to say, their setup and my setup differ. The setup I use is not strong enough it's not as strong as theirs, and so it can't be used to recover this so far. Okay, so I think this is a natural place to start.
Yeah, thank you very much. By the way, concerning this last part, I mean, it's certainly kind of universal framework for some sort of a wall crossing, as you mentioned. Is it possible kind of to develop this sort of abstract formalism, like for counting for Donaldson Thomas or whatever PT invariants? There were some attempts like Joyce, we with Maxim, and finally we kind of with Maxim we extracted this wall crossing part and formulated it as kind of abstract linear algebra structure, which does not depend on geometry. It's equally applied to algebra, to algebraic geometry, whatever. So either kind of, I don't know, abstract setting, because I mean your construction, they have some sort of motivic, like this family of curves, invariants, sort of. There is something motivic behind, but it's not part of algebraic geometry. It's more general. So I'm just wondering if
Yeah,
there.
I'm not sure. I'm not sure what to say.
Because this XGM, it's some kind of, it's very vaguely, I mean, it's kind of how like people compute Donaldson and Thomas invariants. I mean, they find some isolated points in the moduli space, something like these rigid locals where the invariants are known, like equal to 1, and then they move to whatever place they want, doing the wall crossing.
Okay.
And the final answer, it's a sort of appletistic exponent, this expression, which is similar to your last expression. Yeah. Like,
yeah, I mean, so in this Grothendieck group here, I somehow I completely forget the fact that 2C1 plus 3C2 has the same support as 5C1 plus 7C2. They're just completely different cycles from this point of view. And
yeah, you do not introduce that. It's different. I mean, in a sense, in motivic, they also involve kind of use some standard equivalent, like numerical equivalents or whatever, or maybe like, I don't know, homotopy equivalents in the sense.
yeah, I mean that's I mean what I was going to say is there's more equivalents which one should introduce to be able to see this.
Yeah, it's not exact. Of course, it's not. I'm not saying that this is a part of another story. I'm rather asking either an appropriate abstract setup which plays the role of motives. Because I was always wondering why MNOP conjecture can be true. I mean, beyond
that's something which I have no insight to at all.
Yeah, it's certainly different moduli spaces and very specific, this DT or PT invariants. It's kind of looks as a coincidence, but it is not. Yeah, it's interesting, very interesting. By the way, have you written anything? Because I remember I heard you talk about this, maybe a couple of talks.
Yeah, there's a paper in the archive now.
There is, okay, great. All right, let's ask other any questions?
So what's special about dimension 3 other than maybe you only care about dimension 3 because of MNOP?
Right. So one thing which is special is just the formula for the dimension. The virtual dimension of like the moduli space of stable maps is the Chern number of the homology class plus n minus 3 times the Euler characteristic, plus or minus. So, but if n is 3, then the Euler characteristic goes away. So, and that's sort of important. Okay, maybe I should go back to sharing the screen when you want to define the grading on this group. Well, okay, so I guess I didn't really. Everything's Calabi-Yau here, but you shift it maybe by the Chern number. So these Gromov and the enumerative invariants all have degree 0. And if you're in a different dimension, then this sort of it will be ungraded maps. There might not be a good notion of sort of absolute cohomological degree 0. Yeah, I mean, so like if you have a curve and it's multiple covers, you know, the index of the multiple cover versus the index of the original curve. When n equals 3, it's just a multiple. Whereas if n is not 3, then you have sort of the number of ramification points enters, and it's from the index form.
Yeah.
And makes 3 special.
So, Lina, are you happy with the answer? Huh?
Yes, I'm happy. I'm happy.
Yeah, all right. So let's ask, maybe there are some other people who are still not happy, so maybe they will ask. Okay, any more questions to John? All right, maybe other people are silently happy as well. Okay, John. Well, thank you very much. It's very, very interesting, and I'm still not sure I understand kind of everything I wanted. Yeah, this is okay. This is enumerative story, yeah, and you know, for this kind of Donaldson, Thomas, Gromov, Witten, whatever, there is some categorical blah blah blah. You know, either anything which you can say about kind of
Like maybe taking a
universal family. You know, this, for example, PT story, you take, you know, like this DB Koch, properly understood, you take an appropriate T structure, and then you count semi-stables. It's not the universal count, but you can kind of imagine that you consider families of such things. Then, yeah, maybe you local, I mean, the result, I even cannot tell you. I mean, you cannot say that the category is a tensor, some sort of a symmetric power of categories which correspond to some isolated rigid things, but who knows, you know, there is this notion of semi-orthogonal decomposition, which gives you filtrations, and then you can go to the grading, and then it's more natural to look for some symmetric things. So anyway, have you thought about kind of categorical stuff, which is?
I haven't thought at all.
Yeah, all right.
The one thing which, I mean, what I would like to do is remove this, you know, semifinal hypothesis. And I think maybe if one understood sort of blow up formulas or relative invariants, if one does this for relative invariants, it's possible you could, because by blowing up or blowing down, you can change the first Chern class locally.
Yeah, you know that as people somehow became active in this business related to the blow up formula, like Iritania, I don't know, will you be in Miami? They will have this activity. Yeah, and yeah, I heard the talk of Leinster about this categorical things which might be behind of this blow up. I mean, it's quite natural, yeah. But I'm not sure whether they stick with with Fana on. So that's a good question. I don't remember whether they certainly do not like Calabi-Yau for some reason, because because this quantum spectrum, which Maxim kind of is fascinated. Now it's more or less trivial for Calabi-Yau, but for Fana that's fine. So then, but I don't remember what's happened if on the other side for general. Yeah. Okay. Yeah, it's interesting. Yeah, the blow up formula. So that's a good point. All right. More questions? Well, if not, thank you very much. It's a very interesting talk. Thank you. Yeah. And this is it for today and for this semester.